Hello, and welcome to this Beyond Clean virtual conference. The speakers for today's conference, the sponsors for today's conference, and the Beyond Clean team are all so excited that you're here. If this is your first time joining us for a Beyond Clean virtual event, I want to call your attention to a couple of event functions. All of the windows on your event screen are movable. You can shrink them, you can enlarge them, you can move them, whatever you need to do to create the event feel that works best for you. In the upper right corner is a resources tool. Download conference sponsor information and the resources and links that your speakers have provided for you. On the bottom left, you will see a Q&A or question and answer tool. Any questions that you have for the speaker during each session can be submitted to them using this feature. Our speakers today will bring you a wealth of knowledge, and all of their information can be found in the speaker bio tool on the right side of your screen. Along the bottom are the icons for each of the windows as well. Clicking these will minimize and maximize each window. This will be an action-packed conference, and there will be 15-minute breaks between each of the sessions. So feel free to grab a snack, check on the dogs or the kids, assemble a tray, do some jumping jacks, whatever you need to do before joining us again.
All right. Good morning, everyone. My name is Brett Norton from Beyond Clean. And on behalf of everyone on the Beyond Clean team, I would like to welcome you to part 2 of the CBSPD Global Sterile Processing Conference Series. Welcome back to those of you joining us for another Beyond Clean virtual conference, and I would like to extend a warm welcome to those of you joining us for the first time. Thank you for coming, and thanks for being here. Joining me this morning is my colleague, Adam Okada. Adam, we have such a fun day planned, don't we?
Brett, you are 100% right. The Beyond Clean team is honored to host today's event in collaboration with CBSPD. The title of today's conference is Hot Topics in the Heat of Summer. We have such a great lineup of industry experts joining us for a day of insightful presentations and candid conversations about the hottest topics in our industry. I'd also like to extend a huge thank you to our event sponsor 3M for making this exciting day of virtual learning possible. For those of you that are anxiously awaiting your CE credits, after viewing all of today's sessions, you'll have access to the full conference survey and be able to download your CE certificate. Just a couple housekeeping notes. Just remember, if you are having any audio or video issues with On24, browser refresh fixes about 95% of them. If you're having trouble even after that, then I would try clearing your cache up in your settings, browser settings. The downloadable resources are also a tool available for you in the top right-hand corner of your screen.
Awesome. Thanks, Adam. So we are excited you have chosen to kick off your weekend by joining us for this one-of-a-kind educational event. We understand that you probably have a lot going on between work and home, and I just want to say thank you, and I also want to say happy Friday. Thanks again for being here, for being dedicated to education, for doing something that will help you grow as a sterile processing professional. So sit back, relax, and start that sterilizer load. It's time to get this event started. Our first speaker is Dan Kuhl. Dan Kuhl is a managing director of Surgical Holdings. With over 25 years of experience in the medical device industry, Dan has an extensive background in medical device manufacturing and quality management. Known for his keen eye for innovation, Dan's newest project is the sale of orthopedic implant-grade stainless steel in the UK. Dan is the chair of the Surgical Instrument Special Interest section of the ABHI and the co-host of the Deconversations podcast, a podcast focused on sterile processing and surgical instrumentation. Today, Dan is going to help us explore the fascinating world of surgical instrumentation manufacturing. He will walk us through the production processes while providing key care and handling tips to extend the usage life of these labor-intensive creations. Ever wonder how many hands it takes to make a Mayo scissor? The mystery will be solved during this session. So without further ado, let's welcome Dan Kuhl.
Hi there, good morning. Many thanks, Brett, for that introduction. Welcome, everyone, and thanks to everyone in the US and around the world who's listening right now. I appreciate it's very early, particularly so if you're over on the West Coast. So grateful for you tuning in to listen. As Brett said, I'm here to discuss surgical instrument manufacturing, how it's made, and give you some information around that. And please, if there's anything comes up in the questions along the way, feel free to type it up, and I can hopefully feedback on that. So let's start off with how I would describe a recipe, really. So you want to make a surgical instrument, or you're making a surgical instrument that's been out there for a long time. You need a technician, obviously, who's going to make that instrument, the surgeon who's most likely come up with the idea and for that instrument originally. A need, of course, obviously there needs to be some sort of ailment or need for surgery that this instrument's going to solve for you. Materials and know-how, obviously, are vitally important. Having the correct materials are key to a quality instrument, and of course how to make that. And finally, the point that often gets overlooked, particularly by us instrument makers, as I'll mention as I go through, is commercial viability. We have over 5,000 product lines at Surgical Holdings, where I'm the managing director. So not all of those, of course, are as popular as each other. So obviously, when you're making an instrument, it's got to be scalable if it's to be successful. So let's start with this picture, which I guess we could describe as the beauty of a surgical instrument, a nice, bright, shiny, chrome surgical instrument. However, there is much more than beauty to instruments themselves. A lot more goes into it in terms of how they're manufactured and the steel. So although obviously on the face of it, the aesthetic beauty is there, there's a lot more than that, just to the production of them. And there's certainly a lot more than beauty with being a surgical instrument maker. So here I am as a scrawny, relatively ugly 16-year-old, starting out as a surgical instrument apprentice. Alongside me, my colleague Mark, who is one of our most skilled technicians and still is. So this is where I started my journey in surgical instruments, and the insights I'm going to share and some of the manufacturing techniques are things that I learned along the way, and hopefully will be interesting for you. Just to add, nowadays, the surgical instrument maker that I would how I'm referring to them now are generally known as technicians. I guess that's probably the more modern terminology. While I was doing my research for this presentation, I came across a journal article, which I'll show later, from 1989, actually, which is all about the background of surgical instrument making. And I was interested to reflect upon my parents' choice of career for me when I saw this statement from the London tradesman back in 1747, advising parents on the choice of trade for their sons, stating that no special strength was required to be a surgical instrument maker. So I don't know what that says about me, but they obviously thought that was fitting to my career choice. However, surgical instruments are something that I have a sort of fairly long heritage line in from my family perspective. My grandfather's uncle started his first instrument making business back in the early 1900s, and he was joined by his two nephews who trained alongside him. Eventually, my grandfather trained my dad, my father, Philip Call, who founded Surgical Holdings back in '88. And I came into the industry around '95, as I showed you in that lovely picture back a few slides ago. So as an instrument maker, Surgical Holdings is still a surgical instrument maker, repairer. We repair rigid scopes, power tools, and amongst other products as well. I found this fantastic diagram which really breaks down the evolution of the surgical instrument maker. So dating right back to, I guess, the Stone Age, the flint tool maker, obviously using flint to make different tools, and then going into the Bronze Age, the bronze tool maker, blacksmith being a famous trade that's come about as part of metal working and heating up metal and working with metal. And there are other elements to this that are factored in: experts in silver work, the mention of ivory there that used to be used in manufacturing surgical instruments. In fact, I've actually got an ivory handled surgical instrument right here, which is quite amazing. So obviously factoring all these different skills and expertise, we have the more modern surgical instrument maker that has come about, who takes on lots of different areas of expertise. Not necessarily, I wouldn't say an expert precision engineer, but more of a craftsman, because you have to do so many different areas of manufacture to make an instrument, and I'm going to go through those a bit more. So really, a surgical instrument maker is a direct descendant of the caveman from obviously back in the Stone Age days. This is the journal article I mentioned, and I'm happy to share this at the end because it's a fantastic read. The real history around how instrument making in the UK has developed over the last thousands of years. Very interesting, obviously running through Roman times and ancient Egypt, when surgical instruments were well documented to have been used. But in terms of how a surgical instrument maker develops, as I mentioned earlier, being an apprentice myself, here we have a photo of Terry Coe, who's our factory manager and one of our most skilled instrument makers back in 1980, receiving the Souter Prize, which was at the Royal College of Surgeons in London. This was for his craftsmanship on a particular instrument when he was an apprentice. And this is what Terry looks like now. Obviously, you'll see some subtle changes in his appearance, but he's still obviously just as skilled and as valuable as he was back then to our industry. So let's move on now to looking at the origins of surgical instruments. An interesting comment here and quote that the British surgical instrument makers have not, on the whole, been very innovative in their design of products, which may seem a bit harsh. However, looking at a picture here of, on the right-hand side, a modern-day artery forceps that we call a Spencer Wells in the UK, and comparing this to the one that was invented back in the late 1800s, you'll see that maybe not very much has changed from a visual perspective in this instrument. I guess you see, we'll see the introduction of the box joint here, which obviously gives a benefit strength-wise, and a slight change on the rack, or the ratchet as we would call it in the UK. Ironically, I think we're finding now that box joints can prove a little bit tricky to clean, and it may be more advantageous to move back from the design of the late 1800s. But of course, the point I'm making is that a lot of these designs are very similar now and haven't changed a great deal. Of course, other than the introduction of stainless steel in the early 1900s, which makes a significant difference to their cleanability. So just to run through here, historically, surgical instruments have developed over the years, as we mentioned, all the way from Roman times, ancient Egypt, Bronze Age, introductions of different materials being used, coming into more of the modern day era, when now, of course, we have the benefit of laparoscopic surgery and indeed robotic surgery. So, of course, we have in the picture there was the Da Vinci robot, which I've managed to skip on from. But yeah, the devices themselves have evolved, and of course some of the manufacturing techniques have evolved as well. But so what's in the name? Nomenclature of surgical instruments it's fairly self-explanatory, really. And if you look at something like a Spencer Wells artery forceps, generally speaking, the name of the surgeon may be the first word. So Spencer Wells being the actual surgeon who invented the instrument way back in the late 1900s, and artery being the area that the device is used on, and forceps describing the nature of the instrument. So that's generally how things go. So just to give another example, and it starts with a medical issue. Here we've got a visual of someone with obviously a fairly extreme hip issue. So osteo, meaning bone, otomy, to cut into, and ostomy, to create an opening. So if we combine those terminology, here we have a capener osteotome, obviously for use on bone, cutting into and creating an opening. To give some credit to capener, in general, typical surgical instrument maker seems to be very conservative and to have deferred entirely to the whims of his customer, the surgeon. So this was a remark made on this paper back in 1989 that I've referred to, but it's very, very true, and we are guided by the surgeon. Here's Norman Capener, who's an esteemed, renowned orthopaedic surgeon who operated in the West Country of the UK, Royal Devon and Exeter. Obviously, Capener osteotome being one of the instruments he came up with. And this is an example of the type of drawing that we get from a surgeon who might have an idea. I mean, to be honest, this is probably one of the better ones. Fairly detailed with some dimensions on a scrap of A4, and from that, obviously, we have to assess the viability, which materials could be used, obviously how the device is going to be used, and we come up with something like this. Well, this is actually a Whitlow retractor, which is a vaginal retractor that Barry Whitlow, a surgeon from Colchester, came up with, and as an idea for vaginal hysterectomy, and they felt this retractor would aid with that. As an instrument maker, what we have found, and as I mentioned earlier, that commercial viability is a key thing. Again, another quote here. Same appears true today, that the willingness with its British surgical instrument maker continues to produce fanciful and wholly uncommercial instruments to the design of individual surgeons is legendary. So it's quite interesting that obviously over the years, as an instrument maker, a lot of the devices that have come about directly of surgeons' ideas. Some of them may be better than others, of course. And I'd just a comment here, just for further research. I'd strongly advise if you've just got into surgical instruments or sterile processing theatres, whatever operating theatres, to Google some of the names of some of the instrumentation, because you can quite quickly come up with some excellent backgrounds. Jules Emile Peen here, who invented the force of pressure forceps, so basically the artery forceps. You can find out obviously what they achieved as a surgeon and how these instruments were invented. It gives some excellent background around that. So now let's move on to material selection. Here we have on the screen an image that I've put up on presentations before, and I've had remarked as either dinosaur poop or a chicken nugget, but it is indeed a piece of iron ore, which is vital when you're understanding surgical instruments and how they're made. The majority of surgical instruments that you would reprocess in sterile processing every day would contain 70 to 80% iron. So obviously iron that's extracted from the iron ore, plus of course other elements such as carbon, nickel, and chromium. But yeah, you'll be familiar with the orangey colour of the iron ore, obviously, which bears a very, very striking resemblance to the colour of rust. So iron oxide, here's a good few chunks of iron oxide. This is iron in its most stable state. So we've really got to remember that obviously iron in its most stable state is this, and we'll do whatever it can to get back to that. Of course, when we're manufacturing instruments or steel to start off with, the iron ore is smelted down and obviously combined with other elements to make stainless steel. And if we have a look at the world ironing ore map here, you'll see, and this is a graphic that's a few years old, majority of this is concentrated in the Far East now. So it isn't really any great surprise that a lot of the steel now produced is produced over in China, India, Japan, and therefore, as we know nowadays, a lot of instrumentation is also, a lot of forgings are produced over in these areas as well. So this isn't any great coincidence, I mean, being that a lot of the materials are mined and produced out there too. No matter where the materials are produced, standards are vital. And I just draw your attention to ISO 71531 here, which is the international standard for the composition of different materials and steel grades for the manufacture of surgical instruments. So this is standardized throughout the world. It's essential that for a particular instrument, it has to have the right grade in order it to be fit for purpose. And I'll just explain a bit more. It's also worth mentioning in the UK, we have a few fairly outdated British standards for surgical instruments. You'll see there's a standard there for scissors, dissecting forceps, instruments with pivot points. These can contain a bit more detail, such as testing criteria for instruments, but as I mentioned, they're quite old. I believe in the States, you've got your own standards. And in Germany, certainly there are the DIN standards, which are a bit more prescriptive. From a regulatory perspective, we have the CE mark at the moment in Europe, obviously, which is relevant in the UK. Of course, we've left the European Union, so we have our own new regulatory mark coming in, which is the UK CA mark, which has been developed as a regulatory qualification, if you like, for medical devices. So we're not quite sure completely what that will look like at the moment. Of course, the MDR was released in May, and obviously, as a British company selling into Europe as well, we're obviously governed by certain elements of that. So the regulations seem to be changing a lot at the moment, particularly if we're in the UK. So just a mention of stainless steel, obviously it's of vital importance to understand a bit about this, and the history is interesting. That in 1912, Harry Brearley from the Brownforth Research Laboratory in Sheffield invented martensitic stainless steel. Martensitic being the description of the type of stainless steel that we tend to use on instruments. So he was actually trying to design a corrosion-resistant alloy for gun barrels when this was discovered. So that's a fairly interesting bit of history there, aligned with this type of steel that we ended up, of course, being so useful to us. So let's have a look at the composition of the steel here. We have the top four yellow highlighted lines that I've flagged up there are generally the most popular, actually probably B, C and D. What you'll see that's a bit different about them each is that the carbon level, which is C, increases as we go down. And that is because an instrument that's made out of a D needs to be a lot harder than an instrument that's made out of a B. A B might be something that needs a bit more flexibility, such as a forceps, whereas a D, something that's got to do a lot of cutting, basically, and you want to retain sharpness, because the carbon in the steel itself is what allows you to harden it and make the device hard. You'll see also the levels of chromium tend to increase as that level of carbon goes up. It may be to do with additional corrosion resistance as well. So back to our picture of a Kepler osteotome, albeit with a nice medical grade blue plastic handle, but the osteotome itself has a high carbon level, 0.42 to 0.5, and the Rockwell is also hard, of course, because it's going to be cutting through bone, and of course, if it's going to do that, then it will potentially dull on the edge. So obviously, it needs to be as hard as it possibly can. And this is the particular prescribed Rockwell level that would be associated with this carbon. And unless you use this particular steel, you won't achieve that. So obviously, material selection is vital. And just to touch on passivation, in the alloy itself, stainless steel, the martensitic stainless steel, we have chromium. Chromium does things like make the steel look really nice and shiny, but it also delivers this really vital bit of corrosion resistance, which is the process of passivation. So the chromium in the steel reacts with oxygen, creating a chromium oxide layer, which is formed and protects against corrosion. It's very, very thin, and also quite susceptible to damage and scratching. Laser marking could potentially also damage that if it was particularly deep. So certainly something to bear in mind. And just to show you what water on a ratchet on a forceps here, if the water is left on the forceps, it can damage that passive layer, leading to staining, like image such as this. And you also might have heard of pitting. Well, here's a forceps at the end of a forceps showing some real quite aggressive pitting. Pitting is like a cavity in the stainless steel itself. And the reason that generally comes about is just because of the presence of chlorides. So it might generally you'll get chloride in potable water. So I guess tap water where you're not using an RO water treatment. And this is a big consideration for the surgical instrument maker, of course, because we have to ensure that instruments are passivated, and we do the best to ensure that they resist this sort of issue. But sometimes if an instrument is scratched, free iron can be released from the pit, where you see here. Pitting corrosion is highly accelerated if chloride is present. There's essentially the electrolyte solution that the chloride in the water would produce, and the two react quite nicely, basically causing this pit, which can get obviously can get gradually worse, obviously, if it's not dealt with or the instrument isn't replaced. So the anions are attracted to the anode, and it's just essentially something we want to avoid with surgical instrumentation. Here's an example of what chloride damage might start to look like as well. Obviously, staining on instruments here, which is quite a visual thing, of course, can be found in blood as well. And just a reminder, really, that what rust looks like, iron plus oxygen plus water equals hydrated iron oxide, which is rust. So if you've got an instrument that has become damaged, it's leaching free iron, then it will do its best to head for looking like our original iron ore picture, orange, bright red rust, and that will be a natural occurrence. So this is consideration in the UK. Here's actually England and Wales, all of the different potable water sources we have, a variety from rivers, streams, groundwater, and this leads to a massive mix-up of different minerals. You'll see if you're in Cambridge, you have a very high chloride level of 100 versus that of London of 20. So it might be that if you were washing instruments using tap water in London, there would be very, very little risk of pitting on your instruments, but that could be much higher in Cambridge. Generally speaking, in the UK, we have RO steam. I think throughout but in Wales, I think they, other than maybe in 2 hospitals, they rely completely on potable water. So all of these different effects of minerals can really have a dramatic effect on instrumentation, which needs to be considered. And of course, where's this water coming from? It could be, and I'm writing this from the instrument maker's perspective, of course, because if we're confronted with an issue where instruments are rusty, is it from taps? We know that, if you've got RO steam, then could it be that washer disinfectors doesn't use RO water? So all considerations along the way. So let's look now at manufacturing techniques. As instrument makers, we use patterns, and here you'll see a nice selection of mallets here, which are all tagged. So these are in our stores, actually, which hang up by some of the raw material parts. So if we get an order for a particular mallet, one of these patterns will be taken out to go down into the factory to be manufactured. It might also be accompanied by a drawing. Some of the instruments have drawings alongside them as well. But quite often as an instrument maker, you rely on the pattern for, it could be the weight of the mallet, the feel, how well the scissor cuts, how well a forceps feels. A lot of that stuff you can't replicate with drawings. So that's why instrument makers tend to have patterns. And doing the due diligence on your materials as well. As I've mentioned, how important it is to get the right composition so you can achieve, obviously, things like passivation and the correct levels of passivation, hardness. Therefore, you have to make sure the material's right. We do our due diligence. We send our forgings off to be checked to ensure that they're meeting the correct parameters for the international standards. So drop forging is one of the techniques used to make surgical instruments. It is by far the most common because generally instruments are made from forgings. There are other techniques that are used as well, which some instruments may be manufactured completely from CNC machines nowadays. Other water jet cutouts. I've got one here actually for a hip rasp. Could be used. So it's there are a variety of different techniques, but forging is the most popular, and this is essentially what a hammer forge looks like: heating up material and hammering it out into particular shapes that you desire. And here's from our old forge that we have in the factory. These are some of what we call forging bosses. You'll see some of the different shapes and sizes. These aren't in use now, but it's a great piece of history. You'll see what the bows are like. So obviously the steel's heated up and bashed using these essentially templates. And when the forgings are when they're forged, they'll become quite brittle, so they then have to be annealed to make them a bit softer and workable. So when we get the forgings, or if we got the forgings, they're generally very, very pliable to allow for easy machining. So here's an example of 2 forgings, well, basically for a needle holder, so very common. And I'm just going to show you now the technique of what heating material up would achieve. So my colleague here in these photos, which is using an acetylene torch here just for demonstration purposes, but you get the steel nice and hot like that, and then you can work the steel. This is actually in this picture, he's spreading the material to be used for a different instrument, but it's quite a small picture, but you can see he's gradually working it and using a hammer to spread out that material. So it's really the same concept as in forging, obviously heating the material and then spreading it to a shape that you require. There we go. So here's our forging. So on the left, you'll see the needle holder I showed you before, and this is what it looks like after it's then been milled. You can see slot milled in, and obviously the box joint being milled out. These would then be eventually cleaned up, polished. The slot would be opened up, and the needle holder would be articulated and joined up. So, and there's of course a lot other processes involved in that along the way. Obviously, mills play a great part nowadays in allowing material to be removed, and for forgings particularly, a lot of areas of those forgings would need to be milled, things like racks and things, to obviously ensure the instruments are in a suitable condition to be put together and articulated. But as I mentioned previously, CNC mills are often used nowadays to manufacture complete components and instrumentation as well, so that's something to bear in mind. And just to show you what the finished article looks like, of course, we know what a needle holder on the right looks like, and this is what the forgings assembled together would look like. So reflecting back on, as I said, about the instrument maker being a craftsman and not having necessarily superb expertise in every single area of engineering, but we do use things like lathes. So here we're turning up some handles for some osteotomes or some mallets, something like this. So you use the lathe for whichever purposes you would need them when you're manufacturing the product. Depends on what you're making, really. But in this instance, we're turning up some handles from some medical grade plastic. And of course, the more basic techniques, drilling and reaming. My colleague here is drilling some holes on an orthopedic mallet to reduce the weight on it. So yeah, all fairly basic techniques overall that help to manufacture the instrument. And welding. Welding was one of the first things that I learned when I was an apprentice, back when I was 16. I was actually got the job of welding up an instrument that was very, very popular, a veterinary instrument at that time actually, that I was making was horses' tooth rasps. So it was joining up essentially the part that would take the blade for the tooth rasp and the rod. But welding is essentially using a torch to heat up the material to make it molten, and then use a filler rod to join the two materials. And in this picture, we're making some sort of retractors here, where the cap of the top of the instrument is being welded onto the stem. And there's some quite unique techniques instrument makers have as well. This is actually hand chipping. So this is Mark, the gentleman who was standing next to me in the picture at the right at the start, and he's hand chipping a tooth rasp. So with I guess a tool steel tool bit that he sharpened up to a specific shape. So this is for manufacturing these hip rasps, which if you're involved in sterile process, and I'm sure you have nightmares over actually getting these things clean, but they're literally hand chipped. Some you do get some machine teeth, but this is just to really show the sort of skills that we have. And more modern techniques do come into play. Laser welding is a great step forward for instruments, particularly aiding on the sterile processing side of things. Retractors, for instance, they've been a bit of a real godsend, really, because when you're manufacturing a retractor, the ratchet part here that is welded to the instrument. Well, previously it was quite hard to fill the gap around here, but now we just use a simple sort of laser weld to run it around the edge. It seals it up. It prevents any water getting in and any bioburden. Previously, that might have been soldered or they're just left open, which is very, very messy because obviously they can get all sorts of dirt and grime in, and it's generally not good. Finishing wheels. So as part of obviously hand making a surgical instrument, if you've just welded it, then you'll use a variety of finishing wheels. Trevor, one of our polishers here, is using what we call an MX wheel, which allows you to remove weld and dress up the instrument. I think he's making some sort of reamer he's got here, but so he'll remove the weld, and then that's before, I guess, the more aesthetic polishing will be done. Grinding, years ago, and we've still got grindstones. We used to use sit-down grindstones, which take quite a bit of time. They run a lot slower. Now we use essentially linishing. I'm trying to think. We call them banders, but they're very, very. You get different level grits, and they run at high speed on the band and allow you to remove a lot of material. Here we're grinding a scissor up in the picture, but yeah, it's a slightly different technique. So just to mention also specialist scissor sharpening. My colleague Reese in the picture here is sharpening a scissor. There's lots of, I guess, different types of scissor. Particularly, it's worth considering the supercut scissor and how you can't just sharpen it on a normal grindstone, because if you've got a beautiful sort of stilly scissor or something like that, you'll end up ruining it. So when you're looking at a supercut scissor, you've got your serrated edge and a sort of cutthroat razor edge. The serrated edge needs a serrated grindstone to achieve that. So that's part of the process, to have all these different machines which are suitable for these instruments. So setting and bench fitting, we've got an example here and bench fitting is one of these really, really, I guess for an instrument maker, they spend probably 60% of their time at their bench. Got brass jaws in the vise here to ensure that the instruments aren't damaged, and those will be the bench fitting we use for setting forceps, scissors, for setting the scissors. But again, the brass is essentially so you don't get any unnecessary damage on the instrument itself. Plating and what I guess titanium nitride or ceramic coatings are quite common. We see plating in for gold plating for designating on things like needle holders if they've got tungsten carbide in them, or black chrome, as we see on supercut scissors. And this is just a quick rundown. Two gold bows obviously mean tungsten carbide, 2 black bows supercut, 1 black bow in the UK left-handed, 1 black, 1 gold bow supercut tungsten carbide. But people are tending to use these coatings for a lot more uses now. This particular hospital here used a titanium nitride gold coating, so a ceramic coating, to coat all of their instruments for their post-97 patients because they wanted to keep them separate or visually easy to identify from their other pools. So, of course, they're used on things like keris and rongeurs with the advantage of reduced friction and improved cutting. So, actually got a ceramic coated scissor there, which another process. So induction brazing, this is really important for needle holders when you're making needle holders or repairing them, to use an induction brazing machine. This coil, the induction coil, ensures that only the relevant part of the instrument heats up. There's no heat from outside the induction and the outside the induction loop, and you have flux that is applied to the essentially the needle holder insert. And the induction brazing reacts with the flux, and you achieve what you want to achieve. It really importantly not to heat up the rest of the instrument because it could potentially damage it or make it soft. As we know, there are lots of different types of needle holder jaw, which would all be manufactured separately by other subcontractors and then put onto the needle holders. So final polishing and finishing, something that's for me is a bit of a something that's often overlooked. Unfortunately, the graphic is overlapping some of my text there, but essentially the easy way to explain this is the smoother the surface, the better the corrosion resistance. We look to achieve under 0.2 microns in terms of how smooth the surface is. The rougher the surface, the higher the wettability of the steel. So if you drop some water onto a rough surface, it won't flash off. If it's a really, really smooth surface and you've achieved this with some brilliant polishing, then it will flash off, and you've got less chance of that sitting on there and damaging the surface of the stainless steel. So this, I think, moving forward, finishing of instruments is very, very important, particularly when we're looking at things like protein, and to ensure the smooth finish. And this is the sort of thing that we can achieve. This is a duo finish with a bright polish and a what we call a wet bead blast finish on the other side. And to mention vacuum hardening, as I showed at the very start, obviously we have our forgings and they're soft. We do all those different processes at some stage or another on the instrument, and then once it's all finished, you would have polished it up to a significant level. They'll go off. The instruments will go off to be vacuum hardened at another vendor who have these big vacuum hardening machines. The instruments are vacuum hardened and tempered to a really, really tight tolerance. They come back and obviously they're hard and functional for what they need to be. And then we just do some final polishing, what we would call brushing and mopping on, and the instruments would be ready for laser marking. So here we see obviously laser marking, which probably a lot of you have laser markers in your units that you might be using. We tend to passivate after we laser mark. Here are a couple of our tanks that we've got, obviously cleaning and passivation. We ultrasonically clean using the cavitation bubbles in the ultrasonic cleaner to ensure that the devices are obviously really clean and manufacturing debris removed. And then we then passivate. And I've mentioned passivation previously. I mean, it is a natural process, but you can artificially achieve this by using an acid, so nitric or citric acid. We tend to use citric acid. And that's what we're doing here, and that will oxidize the surface of the steel to achieve that corrosion resistance. And that's validated to an ASTM standard, actually. So it could be worth looking at that if you're interested. Packing and labeling, something that gets overlooked, but it's becoming more and more important because certainly from a sustainability point of view, obviously using as least packaging as you can, or if you are ensuring it's recyclable, but labeling as well. Have you got the right devices on there? The right symbology? Is it CE marked? Is it UKCA marked? Does it have a barcode? Does it have a GTIN? It's a lot more complicated nowadays. And of course, this is all part of how the instrument is made, because obviously this is how we present it safely. We don't want to make a really nice, delicate forceps and then we put it in packaging that's not suitable and it's damaged when it comes to be used on the patient. So here I'm just going to run through you how we go from a forging to a finished instrument. Here we have a Volkmann retractor. Can't see it particularly well, but this is a double sharp pointed Volkmann retractor. This is the pattern on the right. As I said, we go and get the pattern. We've got the forging here. We've milled a slot in it up the top. And then there's a lot of bench fitting. So my colleague here is filing the seam from the forging away. You'll see that seam round there. He'll continue to file, taking that away, and then he will also use some emery cloth, sandpaper type material. He'll go on the band, what we call the bander, and take down the material to take it down to size until it looks nice and smooth like this. And then he's going to put it in his vise and with a brass jig, gently knock it over until he's got the desired shape. He'll file that all round into the teeth and the shape of the teeth that he needs, the profile. Then, of course, that will be finished and polished, so it will look something like that. Commercialisation, is just to touch on, obviously, as an instrument maker, you might choose to work with a distributor. You might have your own sales teams. But obviously, it's quite important to decide what you're going to do. Like, are you going to just be a trade manufacturer? Or are you going to have your own catalogue? So all of that builds into part of this, how it's made story, because obviously you're going to make something, you've got to have a suitable chain of customers to sell it to. And just to touch on the variety of different features. So here we have a needle holder. We've got teeth, which are obviously come from a manufactured insert. They're vacuum, they're induction brazed on. The shanks would be set on using our craft skills that I've mentioned, brass jaws, gold handles that are plated, laser etched. Obviously the device is polished. There's so much that goes into each of these devices, and just looking at some of these common features, I won't go through all of them, but obviously box joints are very, very common on forceps, needle holders, ratchets that we see on retractors, teeth, of course, on tissue forceps. So just common terminology that you would see. The same here. Just to highlight atraumatic teeth. So on some forceps, you'll get artery forceps, for instance, will have quite a rough serration, and others that might be used in cardiothoracic tend to have this atraumatic teeth. So the idea being that they won't cause as much trauma to the surface of the tissue. So it's like a reduced surface area jaw, which which will be found on things like DeBakey's, Satinsky clamps and stuff like that. So now to validation, which, seeing as I'm on a mainly sterile processing conference, I've got to actually mention. So why we need to validate, I mean, this is an interesting picture of a Keris and rongeur, which I'm sure some of you would have seen before. It was deemed to be responsible for the carbonised bioburden, deemed to be responsible for a surgical site infection. So obviously, if we're going to make an instrument and make a claim that it's safe to use, we need to be able to ensure it can be cleaned correctly as well. So if you're coming up with a new instrument, part of that manufacturing process is actually, can it be taken apart? Is there something in the design that allows us to take it apart so it can be properly cleaned? And this can be explained to the obviously the technicians who might be sterilising it and reprocessing it. But of course, we would carry out validation on this. It would go off to a lab. It would be tested to check that it can be validated, and then those validation results would be put into the IFU in hopefully an easy to follow way for you guys out there in sterile processing. Finally, protecting and organising instruments. Something I always are quite staggered that if I look at a commercial dishwasher, you've got fantastic options for storing knives and forks and plates and stuff like that, and we never seem to evolve it too much when we're looking at the washer disinfectors. But as an instrument maker, this is something we get often asked to do now. Could you make this set? Could you put it in a basket? Purpose of these baskets twofold: to ensure that the instruments are protected, and to arrange the instruments so there's no shadowing, so they wash as efficiently as they possibly can. So something that that we're commonly asked to do for a variety of different sets, really. And of course, the more delicate the instruments, it might be scopes, it might be laparoscopic instruments. Obviously, significant value in investment there, and really vitally important to protect that, so the instruments don't get damaged accidentally when they're being reprocessed. Just reflecting back to a journal article I mentioned from 1989, the case maker was a separate trade within surgical instruments, a minor specialised branch of cabinet making, and the case maker had two major customers: the surgical instrument maker and the gunsmith, which I thought was fairly interesting, and the second reference to firearms in relation to surgical instruments as well. So, and from the outside, it's almost impossible to distinguish a case made to accommodate a pair of pistols from one made to house surgical instruments. So, I guess if you see a surgeon carrying along a set of instruments, you might know you'd assume that there's instruments in there, but I guess they're saying that it could also they're similar similar boxes made for guns, and we actually have one of those. So this set here is from the early 1900s. It's a fantastic actual family heirloom that we've got that was passed to my father from his uncle as part of that heritage, and they were clearly ahead of their time a little bit. Obviously, specialised instrument making cases. You can take each layer out. Presumably for cleaning. I'd like to think it was for cleaning. Obviously, these weren't made from stainless steel. They're just plated. But yeah, it's a real, obviously, it's a real piece of art, I guess, in a way. So what does the future hold for instruments? Well, I've mentioned that, we are still using a lot of instruments that are from 100 years ago, maybe designed, or 50 years ago. Of course, we're using robotics. So quite proud to have the UK Cambridge medical robot. They have the Vercius, which they're now using or now selling worldwide, obviously alongside the Da Vinci, which is another brand. We proud to be making the baskets for these. So for the arms of the instruments, robotic arms, and the scopes for them to go in to ensure they can be reprocessed. That's a great thing to be involved with. Carbon fibre, I think, is interesting. You'll see carbon fibre perhaps on orthopedic retractors. Obviously, it's radiolucent, so obviously if you have an MRI, it won't show up. It's very, very hard. But when I'm thinking about another material, what's going to be the next stainless steel? Bearing in mind stainless steel was invented early 1900s. Is there going to be something that replaces it? Well, it doesn't seem so at the moment, because carbon fibre, although it is very hard, and it's light as well, and a nice material obviously to use, but it's so expensive that obviously it's got its place on Formula One cars at the moment, maybe not surgical instruments. So just to comment here about nano coatings as well, and this is something that I've worked alongside a colleague on, developing some of the first antimicrobial coatings that we're sort of researching. But to put this in context, nano coatings I find very exciting from an antimicrobial perspective. So imagine the surface of antimicrobial wound dressing. If it's currently coated at a normal scale, increasing this to nanoscale would make this 1,000 times more effective. So if you were to put an antimicrobial coating on a scissor or osteotome or something, or even that kerosene rongeur we showed that had the bioburden in it, then obviously this just gives the patient an extra protective layer if it's got an antimicrobial treatment on it. So that's quite interesting. Medical plastics as well. We seem to be seeing more and more grades of commercial medical plastics coming available. I mentioned some that we use for handles on this, like things like mallets and osteotomes and things like that. So that's something that we're using more and more frequently in manufacture. So to summarize, instruments are crafted by makers, technicians, as we now call them. The names of the devices come from their inventors. And is there a commercial viability when we're asked to make an instrument? That's a big consideration now, more so now than ever was, really, because of the regulation. I mentioned the MDR and UKCA previously. Like 15 years ago, someone wants something made, yeah, you do it, but now you've got to really consider how much this is going to cost to regulate. Fair enough, adding on this other device, which might be used by 2 or 3 surgeons, but is it actually going to be commercially viable? Iron makes up the majority of the composition. So, when you're trying to understand why instruments may go rusty, this is a key point to remember. Everything's got iron in it. Obviously, if it's a decent quality steel, it will have the international standard, and it will follow the international standard and have all of those correct composition elements in it. Passivation of the steel is crucial. If you're going to ensure that the instrument is as corrosion resistant as it possibly can be, then that's a really, really important process. As I mentioned, there's a validated process to follow. And the majority of instruments are from forgings. I didn't want to leave out other types of instruments and parts of instruments. I mean, we have things like hollow handles that are used that are like sheet metal that are pre-formed. I think I mentioned water jet, laser jet. There's lots of different types, but the majority of them will come from forgings. Many instruments of designs have not changed, but the technology to manufacture them has. I mentioned things like laser welding and coming about and being used nowadays. And it's a variety of craft processes that are used quite often by the instrument maker at their workbench: filing, bench fitting, bending, setting. So it's really, really, really truly is a craft industry. And something I feel, and moving forward, we've got other things to discuss, but consideration's got to be given to sustainability and safety. So safety from the perspective of reprocessing. Can things reprocess safely? Can they be validated? Can you prove they're safe to use? But also sustainability. So that's giving support to customers and end users on what to look out for repair, ensuring instrument longevity, how long things are going to last, why things might be staining. So giving all that guidance, that's all part of the package. For me, this is the overall thing of how to be an instrument maker. Thank you very much.
All right, Dan, thank you. That was awesome. A lot of good information in that presentation. And for our audience out there, this presentation will be able to be downloaded, and you can access the slides and go back to, check on what you were interested in and just to review the whole presentation. And Dan, I honestly think that this is really crucial when it comes to sterile processing, because there are so many complexities with these instruments, right? It's the materials, and as things have gotten more advanced with the robotics and the scopes, there really needs to be a real understanding of the entire process. And I think that goes in tune with manufacturing, knowing how these instruments are made, knowing what kind of materials you're using, and because that has a lot of effect on how they're cleaned. and how you guys build your IFUs. So I think it's very crucial that this topic was discussed, and thank you for doing that. We've got a fair number of questions, so I'll see if we can knock out a few in 5 minutes. Some good ones here. Let's see. So how is the passivation layer applied on an instrument?
Okay, so I think some of the questions probably came through, and then I'll maybe answer them a bit later on. But I mean, passivation is a natural phenomenon, I guess. Probably best way to describe it. It's the advantage of having chromium in the stainless steel, and the chromium reacts with oxygen and creates chromium oxide on the surface of the steel. So that is how it's created. As a manufacturer, you can artificially create that by performing a process called passivation, which is, we use citric acid because it's safer for our employees. Some people might use nitric acid, which is quite nasty stuff. We used to use it, we don't anymore. It involves taking the instrument, dipping it in the acid for a prescribed time. Generally, that acid will be heated, and then it's taken out and rinsed, dried. That's it. There we go.
All right. Seems pretty simple.
Well, it's similar. It's similar to, I suppose, some of the treatments that the guys are doing in sterile processing. Really, like ultrasonic cleaner. It's in an ultrasonic cleaner, so same principle, really.
Oh, okay, interesting. Is aluminum commonly used for coating instruments?
I think it's used in the titanium nitride coatings. So things like the ceramic coatings, it's an element that's used partly in some of those. I believe, I'm trying to think of the makeup of the black ceramic coating you get on kerosenes. I think that has an element of aluminium in it, or aluminum. But generally speaking, no, it's not used as a coating. Where you'll probably see the most aluminium used in sterile processes is in your containers. So that they're generally all aluminium, and they are coated, so they get color coated. So that's not, you see too many instruments made from aluminium. Maybe some retractors, some cardiothoracic retractors, because they're light, but yeah, not too many.
All right, great. So this one is interesting because I think when you're talking sharpening and repair and material breakdown, how often can, say, scissors be sharpened? Is there a number that you put on that, or do you have a gauge on how that is measured?
No, not really. I know that's completely unhelpful, but all I would say is it really depends on the skill of the person sharpening them. If you've got someone who's not particularly skilled, then once or twice. But if you've got people who actually know how to manufacture the instruments and you can sharpen them correctly using the correct machinery, then yeah, I mean, we've seen scissors in circulation for like 10 years or longer. Yeah, so probably not the answer that's going to be particularly helpful. I mean, what is interesting actually is in the UK we don't have any testing on scissors in sterile processing, so it's all down to when the surgeon says they're no good. But in the US, I believe you have prescribed maybe some testing materials and things like that. So yeah, I guess with a combination of using those, sending them for resharpen, that's the only really way to determine if they're suitable.
Right. Good answer.
Yeah.
Let's see here. Here's a good question. So is there any way to improve, I guess, and see the new creation of instruments in the future for newer surgeries? So I guess the way I interpret that question is, I guess, giving more education and training for these more complex instruments and newer instruments that are coming onto the market. Is there a way that you would suggest, or are you guys looking at doing that, or do you do that as a company? So
do you mean like looking at obviously instruments coming out and how best we how would we prepare for manufacturing them? Is that, I'm not quite sure.
Well,
I understand the question.
Yeah, I'm looking at this question, and it seems that the way I'm interpreting it is looking ahead and providing training and education in terms of being proactive, so to speak, and making sure that surgical techs and SPD techs are having that training ahead of time before it's actually widely used in the market.
Yeah, well, I think it's interesting because obviously, the robotics side of thing that's come out, or obviously that has been used for a number of years across the world, and we've got this new machine in the UK that's being used, and it's quite interesting. I think they really early on engaged with the sterile processing community, so not just from a perspective of here's this new device, get on with it. I think there was a real trying to go and talk at events and speak about what they were looking to achieve, and not just from the surgical outcome perspective, but from how we were going to ensure that the full circle was there, that it could be reprocessed safely, and this is why, and this are the steps that we had taken. So, yeah, I think if I was a sterile processing technician and I was looking to sort of try and get ahead on, what might be coming out there, yeah, all I can suggest is you look out for conferences like this and really try and take on board as much information as you can, and also then feel once you've got the education. I know a small bit of education can be dangerous, but it's always worth asking the questions. To why is this laid out in this tray, and it's his material. I think it's always good to broaden your understanding, and if you're reprocessing instruments through washer disinfectors, the more knowledge you can have, the better, because as I've mentioned, there's so many complexities with these stills and the materials that are used to wash them. Does that make sense? I think I'm hopefully getting the gist of where the question was.
Yeah, no, I think that's a great answer. And to that point, I think we are at time. So I'm going to extend a huge thanks to you, Dan, for joining us across the pond. I know it's a little later out there and it's early here, but I really appreciate you joining us all the way from the UK. And it's been a pleasure. And a couple of quick things here is we didn't get to any of the questions, and we did have some great questions come in. We'll make sure that Dan sees your questions, and you can also connect with him via email or LinkedIn from his contact information here on the screen. After this session, your screen will automatically transition you to the next session. But as a reminder, there is a 15-minute break between each session throughout the conference today. If the registration appears and you've already registered, please click the already registered link and enter your email address to enter the event. You will be able to access the CE survey and certificate by visiting beyondclean.net/virtual events, and will be automatically transferred to the survey page at the end of today's conference. All the sessions will be available to you on demand to share and view after today's live event. We're so glad you guys are here. Thanks again, Dan, and we'll see everyone in about 15 minutes.
Thank you very much. Thanks for the opportunity to come and speak to you guys, and enjoy the rest of your day. Enjoy the rest of your conference. Thanks.
Thanks, Dan.
Take care. Bye-bye.